Hi everyone, I'm Romain Cosson, and this is joint work with Xingjian at MIT and Christian Coester at Oxford. So I will summarize the main results and idea in this talk in just one slide from a simple example, which is Mario. So Mario is a character that has to go through a 2D world as fast as possible, and if it could see the entire world, then it will use a shortest path offline algorithm and would output a path at like this blue path. But the difficult thing about Mario is that you can only see a few blocks ahead, so Mario has to use an online algorithm as it only gets more information about the world if it progresses. So the real path that Mario is going to use is going to have to backtrack sometimes because it will reach dead ends, and it will be this orange path. And when you want to evaluate how good is Mario's algorithm, then you typically want to compare the orange path, the orange cost, to the blue cost, the optimal cost, and that is done through a quantity that is called the competitive ratio, which is the ratio between the cost, the distance of the orange path, and the distance of the blue path. And this is the quantity that really characterizes the difficulty of this problem. Now, in this talk, we will see that the competitive ratio for deterministic algorithm is equal to 2w minus 1. So the W here is going to be the width of the screen. It's the number of blocks on the vertical, the maximum of blocks that are aligned vertically. And for randomized algorithms, we will see that there is actually a much better algorithm that has a competitive ratio in log squared W. And the best lower bound we have for this problem for now is in log W. So there is still a gap for randomized algorithms in our understanding of the problem. Now, what is the formal model for this problem? The model is inspired by a problem introduced by Papadimitriou and Yanakakis, and we call it unweighted layered graph traversal, and I'll come back to this name. But just for the notations, we have a tree, so we can focus on trees because without lots of generalities, trees are just as hard as graphs, and we will denote by n the number of nodes and by d the depth of the tree. And importantly, we will have this notion of layer, which is noted by calligraphic L, and the layer D corresponds to all the nodes that are the same depth D. So you initially have layer 1, layer 2, layer 3, and so on, that you can see on the right of the screen. And the width of the graph, or of the tree, is going to be the maximum cardinality of a layer. So in this example, the width is equal to 3, and the problem is online because layers are revealed one after the other. So in this example, say the first layer is revealed, Mario has to move to some node, second layer is revealed, same thing, then the third layer is revealed, Mario can move here, and so on. Maybe Mario has to backtrack at some point. If you look at this specific path that Mario just took, it made 15 moves, and the optimal cost was equal to 5, it was the distance, the depth of the tree, so this specific path is tree competitive. Now, it's easy to notice that the optimal cost, is equal to the depth of the trees, and that n, the number of nodes, is at most w times d, because there is w nodes at each depth. So if you do depth first search, and depth first search goes through all edges at most twice, you have a 2w minus 1 competitive algorithm, like for free, and that's super simple. I'll come back and explain more exactly where this minus 1 comes from, but for now, let's stick with the fact that depth first search is already order W competitive. Now, it's actually quite also easy to see that depth first search is optimal among deterministic algorithms, and the main result of this talk is an analysis of randomized algorithms. Now, the reason for the name of this problem is that the problem that was introduced by Papadimitriou and Yanakakis is very similar. It's called layered graph traversal, so without the unweighted part. And the difference is that the edges, so it's the same feedback model, but the edges are weighted. And actually it changes a few things. So for instance, opt becomes the weighted distance, the smallest weighted distance from the root to the last layer. And in this case, for instance, it's equal to 2. So opt is typically much smaller, so it's harder to be competitive for this problem. And one way to see that is that DFS has an infinite competitive ratio. So say there's one path that is extremely long, maybe your DFS agent is going to take it, whereas there is a much shorter path that it will never see, and that will be equal to opt. So this was the problem that was initially studied, like weighted layered graph traversal. It was studied extensively in the 90s. So first, for deterministic algorithms were studied. So now the problem is nearly closed. Deterministic competitive ratio is known to be of order roughly 2 to the W. This uses recursive algorithms, and there is a series of papers on this question. And also, problem of randomized algorithms took actually much longer to solve. So the first breakthrough was in the 90s, where Ramesh showed a polynomial algorithm in W to the 13, but also a nearly quadratic lower bound. And it took actually 20 or 25 more years for Bubeck, Coester, and Rabani to settle this competitive ratio to be equal to W square. So there's two papers doing that. There's one upper bound in W square that uses the mirror descent framework. And there is also a lower bound that is in their paper on the K-server, the randomized K-server conjecture is false. That's the name of the paper. It proves the lower bound for the K-server problem and also for weighted layered graph traversal. Now, in fact, unweighted layered graph traversal was not really studied until quite recently. My intuition, the reason why I believe this is the case is that it's very easy to observe that depth first search is 2W minus 1 competitive, but it's actually pretty hard to get any improvement over depth first search. So last year with Laurent Massoulier, we showed that it was possible to obtain at least some improvement because we found a square root W competitive randomized algorithm. And now this talk actually improves the square root W algorithm to log squared W, and also provides a simple log W lower bound. Now for the remaining of the talk, I'll talk about two things. First, I will give a quick warm-up to explain the lower bounds in 2W minus 1 for depth first search. So the deterministic algorithms, why depth first search is 2W minus 1 competitive, and also the lower bound on randomized algorithm, why any randomized algorithms must be at least log W competitive. And then I'll go through the main results, explaining why, how our log squared W competitive algorithm is defined. Okay, so the first thing is to prove that depth first search is indeed 2W minus 1 competitive. So I think the easiest is just to take an example, and the proof should be very straightforward from this example. So in the first round, you have to pick a node, and in the next round, you pick another node, and so on. And you notice that if you always do depth first search, meaning like if you always turn right in some sense, then you go through each edge at most twice, except the edges that are on the shortest path from the root to the last layer. These edges can be traversed at most once. So overall, since they are at most 2W times D edges, then, W times D edges, then you get a factor 2 on every edge except those on that shortest path. So that gets you the 2W minus 1. Now, actually, DFS is optimal among deterministic algorithms, and again, that's pretty simple to prove. So let's consider a specific instance, which is this instance, which has W independent path. Now, in this instance, any deterministic algorithm has to go to some leaf. For instance, the algorithm is going to go to the leftmost leaf. Since the algorithm is deterministic, we know where the agent is going to be on this specific instance. So now the person who designs the instance can just delete the leaf where the algorithm is, and the algorithm is going to have to go to some other leaf. Okay, so that's exactly what the algorithm does. Now the algorithm is to some fixed deterministic leaf, and again, the designer of the instance might just kill that exact precise leaf, and the algorithm has to move again to another leaf, and so on, until it reaches the last layer. Now it's straightforward from this instance to see that the number of moves of the algorithm is at roughly 2W minus 1 times opt. So non-deterministic algorithm can be better than 2W minus 1 competitive. Now, last lower bound I wanted to mention is a randomized lower bound that can be no better than log W competitive. So again, the instance is pretty similar, except that now what happens is that you don't know the position of the agent for sure, but you know a probability distribution on the position. And since there are W branches here, one of the branches must have probability at least 1 over W. Like, it's impossible that all branches have probability less than W. And you take one of these branches that has probability at least 1 over W and you delete that branch. Okay, so this probability mass has to move back to the other branches. And now, since there are W minus 1 branches, one of the branches has to have probability at least 1 over W minus 1. And you delete that branch as well. And you do that iteratively until you have just one branch left. And if you do this, you notice that the cost is at least the sum of 1 over I times D, the optimal distance. So this gives you this is where the log W comes from. So that's very straightforward lower bounds, and that's it for the warm-up. Now we can move on to the main result, which is the description of the algorithm that is log squared W competitive. So the first thing is a surprising observation, a surprising fact. It does not seem that there is a naive or very simple randomized algorithm that does better than DFS. I mean, if you have an idea of one that could work, then I would be extremely interested. So the algorithm we have is actually very simple, but it's not super naive, because it's an algorithm that maximizes the entropy of the distribution. To be more precise, the algorithm is going to define a random position x of d. So d here is the layer. So in the example on the right, d is equal to 3. So you see all nodes on edges up to depth 3, and you have to define a probability distribution on that third layer. And so for leaf L in the third on the dth layer, we denote by x L of d the probability that the agent is at L at depth d. Okay, so in this example here, like, you would have 5 over 11 probability of being on the left node, 3 over 11 to be on any of the two other nodes. Now the way x of d is going to be defined is that it's going to be defined as the minimizer over all possible probability distribution on the current layer, like so calligraphic P on calligraphic L of D denotes the probability distribution on layer D. So it's a minimizer over this probability distribution of some convex regularizer, and this regularizer is defined very simply as being the sum of FU log FU, where FU is for edge node of the tree the probability of being below U. So the sum of XL for L below U. So to be more precise, this is an example. Like, for every node, you define the probability of being beneath that node. So you have these these green numbers that are written here, and this phi of x that appears is just the sum of FU log FU. Now, if you notice, if you pick all nodes, if you pick all nodes from the same layer, the probabilities that are associated to them, they sum to 1. This is because, like, these F define a flow of probabilities that goes from the root to the leaves in some sense. So you could rewrite this regularizer as being the sum of the entropies of the probability distribution defined on each layer. And the algorithm is just the minimizer of that entropy. So the intuition for this algorithm, I believe, is that we want to make the position of the agent unpredictable for the adversary, but this has to be true not only on the last layer, but it has to be true at all scales. So that's why we sum entropies over all layers. Concretely, to have a concrete example, perhaps if the tree initially has just 4 children, then the probability are going to be split evenly between these children. But then perhaps at the next round you observe this, and the probabilities are going to change a little bit to give more weight to the right leaf, and so on, until you reach the last layer, and then the only probability distribution that's possible assigns the cost of 1 to the final node. Now, it turns out that our algorithm is very related to mirror descent with an entropic regularizer. So this slide is for specialists who want to understand the link between our algorithm and that more general framework that was used successfully for many other online problems. So by definition, our probability distribution is the minimizer of this convex function over probability distributions. And by optimality, that's the KKT conditions, the gradient of the regularizer at x must be in the normal cone to the probability distributions here. And now if you differentiate, so d here has to be an integer, but just assume for now that it is a real number. If you differentiate this equation, then you get this classical mirror descent equation that the Hessian times the derivative of x belongs to the normal cone, which people call the mirror descent scheme, and which has been used successfully for the K-server, metrical task systems, and other problems. So in some sense, our algorithm is a variational or integrated expression of a mirror descent scheme. And the nice thing is that it is extremely simple. It does not imply any other deltas or any other tricks in its definition. But perhaps at this point you're wondering, like, what about the crown? Because the title of the talk was Unweighted layered graph traversal, so we talked about that, but passing a crown via entropy maximization. So just to justify the name of the title, just let me introduce this simple analogy. Suppose you are the king or the queen, and you need to design a rule to pass the crown, or perhaps also a state secret, through the family tree. And clearly, the crown creates conflicts when it travels a lot from distant relatives, and also secrets get corrupted if they travel a lot between distant relatives, so you want to avoid to have the crown move too much. And also in the model, you assume that the future of your family tree is unknown, so you have to design a rule that is robust to whatever happens to your family tree. Layers will correspond to generations, obviously, and the current rule is just you give the crown of the secret to the eldest child, or perhaps to the closest living relative, and that rule is actually equivalent to depth first search. Now, a competitive rule will be to give the crown to make sure that the distribution of the crown maximizes the entropy at all scales. So I encourage you to have a look at the paper. We also show the connections with other problems, especially learning augmented algorithms. So to conclude, in the paper you will find also an expression for the probability distribution at layer D, a simple expression for the derivative of that distribution, and perhaps also some new perspectives on the mirror descent scheme. And the next possible steps are to close the gap between the lower bound and the upper bound. Perhaps it will be also possible to do some average case analysis to study like algorithms that are good on random trees. And natural other question is, can you also simplify mirror descent scheme in other classical online problems? Thank you very much for your attention, and have a look at the paper.